right? So we're all here for Utkarshani's proposal defense. Go on.
Yeah. Thank you, everybody, for joining me for my defense on the topic Causal Neurosymbolic AI, synergy between Neurosymbolic AI and Causal AI. My committee comprises of my advisor, Dr. Amit Sheth, Dr. Marco Valtarda, Dr. Michael Hunes, Dr. Valerie Shallon joining online from Wright State, Dr. Corey Henson joining online again from Bosch Research Center at Pittsburgh. My dissertation aims to address this hypothesis that can neurosymbolic AI framework be adapted to support causal AI tasks, which is divided into 3 sections. So does it provide us an enriched representation? So can we transform and embed the knowledge from causal network into a knowledge graph? Does the use of hyperrelational knowledge graph provides better contextual information for causal representation? In terms of inference, can we learn from incomplete causal network, which is mapped to the knowledge graph completion task? Can causal weights on the causal relations be used for the link prediction tasks? And can prior knowledge, in our case, be used for the causal link prediction tasks? The further analysis inference task, which would be addressed, but not today discussed in this proposal are, can backdoor path elimination within the causal neurosymbolic framework removes the bias in the causal AI task? Can contextual information using hyperrelational graph improve the performance of the AI task? These would be evaluated on causal AI task within this framework based on the causal Markov assumptions. And we will prove that does integration of these causal weights on relations improve the performance or not? Does adding prior knowledge or domain knowledge improve the performance of the causal AI tasks? So the motivation behind this work is to build intelligent machines which can be taught cause and effect. So talking about general intelligence. Yeah, so to achieve artificial general intelligence, we need to have machines which can reason about causal and effect relationships in the model. So this is true, specifically true for safety critical domains such as healthcare, autonomous driving, smart manufacturing, which needs a causal network of the concepts and relationships happening in the world. So if you look at the image in the middle on the left-hand corner, you'll see this is an image of a stop line marking with the pedestrian are crossing the road at the stop line marking, there's a car which is stopped. So we as a human understand this inherent causal relation that a stop line marking would eventually cause a vehicle to stop and a stop line marking would eventually cause the pedestrian to walk. So these causal relations are not present in the autonomous driving domain or in the observational data that has been captured. On the other hand, we see that this is an image of a smart manufacturing assembly pipeline, which assembles a toy rocket. So in this case, we want to know these or understand this causal relations between what would happen when something has gone wrong. So can we do the root cause analysis or can we do anomaly prediction and give a causal reasoning about why did that anomaly happen? Also in the case of healthcare, given the symptom, can we predict or can we understand or know the cause of the symptom being observed? So understanding causal dependence among these individual components and overall systems, if we have the understanding of causal network, we can be better prepared by doing counterfactuals for the unforeseen circumstances. Also, current machine learning models are just based on correlation data. If we want to do causality, we need to have an understanding or a framework to have a causal network. So learning causal network, however, using just the observational data at times leads to incomplete network due to missing observation. So the real world data sets out there do not have the complete observation set for the events or activities occurring in the world. Prior knowledge from the domain expert. So at times, structured learning algorithms uses prior knowledge from the domain expert to learn these causal networks, which in critical domains such as healthcare, autonomous driving, and smart manufacturing, where you have huge amount of data, access to domain expert, and those knowledge becomes expensive in terms of both cost and time. So we propose this approach of knowledge graph. So instead of domain experts, now can we bring this domain knowledge used from the knowledge graph, which will also give us the context as well as solve the problem for missing observations and unavailability of domain experts. So I talked about incomplete, that we have missing observations. So this is a work which is done by my fellow colleague. In their work, they have noticed that the real-world benchmark, even the real-world benchmark data set has approximately 12% of missing observations into the data set. So obviously, if we are going to learn from that observation data, we are going to learn an incomplete causal network. However, in our approach, if we enrich the domain knowledge, the contextual information, the representation of weights and the causal relations into the causal knowledge graph, and then use the knowledge graph for the task of completing the causal network, will give us a better understanding, better explainability, and enhanced representation of causality. The current causal representation in ontology and knowledge graph. So the first time, one of the first time the causal relation was talked about was in the Dolce Foundation ontology, which defined this causal relation between two events, where one event is changing the characteristics or the features of another event. Another work which talked about causality in the knowledge graph was in CausNet, which extracts relation from text causal relations using linguistic patterns and represents causality in terms of binary relations A causes B, and also in terms of chain relations such as A could cause B, then B could cause C, and was the first in the knowledge graph to introduce this concept of mediator. So in this chain relation A to B to C, B is a mediator for the relation shown above. The second work that has used the causality concept was on Wikidata-based knowledge graph, which extracted news events for news event analysis and forecasting its potential effect. So the image on the right has this represented causality in terms of has cause, has effect relation, which is still a binary relation and does not captures the context or the mediator information in this case. The causal event pattern, which is an ontology pattern on the left, captures causality in terms of has possibly causes relations and possibly causes concept in the ontology. So far, causality is majorly represented as a binary relation of A causes B. We introduced this framework, Causal Neurosymbolic AI, which is a fusion of causal AI and neurosymbolic AI, which combines the strength of causality, neurosymbolic AI, and symbolic neural networks and symbolic representation and reasoning. So we have two arcs in this framework here. So the one goes from causality to neurosymbolic AI, where we use the representations from causal AI, that is the causal network, which is being transformed into the symbolic AI, into a knowledge graph, and it uses the techniques from, and then transformed into the embedding space and using the techniques from the embedding or the neurosymbolic methods. The bottom half of the bottom arc uses the representations from neurosymbolic AI and the techniques from the causal AI. The dissertation I'm proposing, focusing on my work, focuses on the top half of the curve, which uses the causal representation and techniques from the neurosymbolic AI domain. So some of the benefits of causal neurosymbolic AI are explainability. So combining causal models, symbolic reasoning with neural networks to make decision-making process more transparent. It provides understandable explanation for predictions made by neural networks. It leverages causal inference to improve the robustness of AI models to changes in data distribution, enhance generalization by incorporating prior knowledge and causal relationships. So if we learn a causal model, let's say something which has been trained in terms of autonomous driving, a Ford car is trained in US, it can easily be transported, or the model can easily be transferred to a GM autonomous driving domain, or a car with causal, or the model with causal relations of that at a stop line marking or at the stop sign, a car will stop, or at the traffic light, the car will stop. That model can easily be transferred to other domains or other continents, Asia, where those causal relation would still hold. It can help us with intervention. So develop AI systems that can predict the impact of interventions and make informed decisions to achieve desirable outcomes. And integrating causal reasoning into neural networks will enable dynamic adaptation to the new environment or tasks. Some of the challenges in this approach is complexity. So integrating diverse approaches require managing the complexity of combining different types of models and reasonings, data requirement. So effective causal inference requires rich, high quality data, which may not always be available to us, which has the problem of incomplete observational data. Scalability, so ensure that the integrated model can scale to handle large data set and complex tasks. So causal neurosymbolic AI methods of this framework aims to create systems that are powerful, efficient, interpretable, and capable of reasoning about cause and effect. Some of the assumptions that we are making moving forward, that causal networks are inherently incomplete. The goal is to use this incomplete causal network as an input to knowledge graph creation, use the enriched representation of causal relations in knowledge graph, and transform learning from incomplete causal network to a knowledge graph completion tasks. The aim is not to learn or not to do a causal structure learning from the observational data, but on compare with the traditional causal discovery approach, but enriching the knowledge graph representation with the known causal associations and predicting new causal relations and using that. So this is my thesis statement, that application of causality to solve problems in real world settings require a synthesis of causal concepts with domain knowledge. A causal neurosymbolic AI approach that fuses neurosymbolic AI with causal AI will provide an effective mechanism to transform causal concepts and information to neurosymbolic AI representations to enable advanced expressibility and explainability, leverage neurosymbolic AI representations and methods to solve causal AI tasks, enhancing robustness, evaluate the methods, and ensure satisfaction of causal assumptions and constraints. Following on my research contributions so far during my journey, so I worked on K-Health, where we developed a framework for self-monitoring and providing personalized Bayesian inference for pediatric asthma. This work motivated me to work on causality, where I wanted to understand what is the cause of a symptom being experienced by a patient. I also worked on industrial knowledge graph creation for interoperability. My current work on causal neurosymbolic AI has been transferred into these publications, but some of them are under review, some are already published. For this work, I'll be focusing on causal link prediction causal link prediction, and these two publications, which lays the foundation for this work. So here's an outline of my presentation. So I will be talking about representation. So by representing of causality from causal Bayesian network into a knowledge graph. So given any application domain, you can transfer that domain into a causal network and then use the causal network to enhance the knowledge graph, causal knowledge graph. Expression and inference. So knowledge graph embeddings for causal link prediction. Evaluation using Markov-based assumptions for causal link prediction. And I'll show the application of my work in autonomous driving and smart manufacturing. So a primer of causal concepts, some of the concepts that I'll be using throughout this presentation now on. So the first one is causal network. So a causal network is a causal Bayesian network where the nodes represent an event and the edges represent a causal relationship between them. Each node has a causal role in terms of a causal relation. So there are three roles which are defined: treatment, outcome, and mediator. So treatment.
Question?
Yes, Dr. Humes.
Could you back up 2 slides?
Yes.
Okay, what there? So the beginning of your statement, it says causality requires causal concepts.
Yes.
That seems to be vacuous. There's can you think about fixing that? I mean, there's sort of no reason to say that, and that can't be part of a thesis because it's already true, even before you begin.
So are you talking about the first sentence which says requires a synthesis of causal concepts with domain knowledge?
Right. How could that possibly be false?
So if you want to understanding causal concepts, it can be, it helps if you have some context information at place. So the domain knowledge brings that context information where you can have a better understanding of these of a causal application.
Right, I understand that, but the entire sentence is problematic for me. So, can you express a causal concept without any domain knowledge? So, here's a causal concept. Smoking causes cancer.
Mm-hmm.
Smoking is domain knowledge. Cancer is domain knowledge. That statement of causality is represented in domain knowledge. I can't imagine how you could express causality without domain knowledge. So putting causal concepts together with domain knowledge, it's impossible not to do that.
Actually, Utkarshani, let me just intervene here a bit. Are all expressions of domain knowledge necessarily including causal content? For example, the domain knowledge that we have for treating psychiatric disorders, does that have causal knowledge in it?
Not really.
Some of it might.
It might, but often, at least in my experience, the explicit articulation of domain knowledge is, in fact, missing some of the causal and constraint knowledge that supports a particular procedure. That's the way I've seen it.
Okay. So, Valerie, what you're saying is valid, that domain knowledge might not have causality. Adding causality to domain knowledge might be a better model.
That's
So,
the way I read Nini's, Utkarshani, sorry, Utkarshani's thesis.
right. So that would be a much better way of saying it, that simply domain knowledge, you know, Joe is 6 feet tall. That's domain knowledge. There's no causality there. But sort of enriching domain knowledge with causality can lead to better mental health treatment. Great. But saying that causality requires causal concepts is a vacuous statement. So I would like this to be expressed better, and in fact, in accordance with what you just suggested, Valerie.
So Dr. Hunes, this statement is made in terms of real world settings, that just abstract and causal relations or application of causality in real world settings would also require not just the causal concept, but also the domain knowledge associated with that real world setting. So for example, in case of autonomous driving, let's say, you have the causal concepts of stop line marking, causing the pedestrian to walk, but in context of that domain. That's how I frame the sentence.
Right. I don't think real world is meaningful. You could be talking about unicorns, and unicorns are required to have horseshoes so that they don't hurt their feet. And so there's some causality involved with unicorns, even though that's not real world. So being real world is irrelevant. So sorry to dwell on this, but because this is the basic thesis of your entire dissertation, it's important that it be word for word correct.
Mm-hmm.
So we probably, I've elaborated on this enough, and so please continue on from where you were.
Thank you for that comment, Dr. Nunes. I'll think about it and I'll get back to you on that.
So can I ask a point of clarification on that? So just thinking of the example of smoking causes cancer. I mean, I guess you could say that's domain knowledge, or you could say that those are just labels, right? That the machine really has no understanding of. I mean, my understanding is the domain knowledge comes when you bring in all of the other information we know about those labels or terms, and you integrate it together. So my understanding is more along those lines, where you're kind of providing additional context and knowledge about those terms that are connected through the causal relations. But maybe I'm not.
No, I think you're definitely correct. I think the richer a representation, then that can lead to more powerful analyses, more powerful conclusions, more powerful understanding. And so context is crucial. And the more context that can be provided, then again, the better problems can be solved, or more understanding, and so on. So that's all part of it. And so the entire expression of the knowledge in the domain includes all of that. But importantly, it should include causality. So the domain should include causal knowledge. But the causal knowledge doesn't require, I mean, it's said backwards. It says causality basically requires domain knowledge, and it should be that, rich domains require causality knowledge.
So are you saying that
Let's come back to that because we want to discuss.
I'll come back to that, Dr. Hunes.
Yeah, please do. Sorry.
So we talked about the outline. So primer on the causal networks. So each node in a causal network can have a causal role associated with it with respect to the causal relation. So there are three types of causal roles: treatment, mediator, and outcome. A treatment is the initial event which is responsible for the occurrence of some subsequent event. An outcome is a final event which occurs as a result of treatment or the mediator. And a mediator is an event which occurs as a result of the treatment event. So for example, if we take this causal network in account, for the relation C to A, C is the treatment, A is the outcome. However, for the relation CAB, C is the treatment, B is the outcome, and A is the mediator. For the relation CABD, we can say C is a treatment, D is the outcome, and A and B serves as an intermediary nodes or intermediary roles, mediator roles. Another concept that I'll be talking about was causal effect weights, which is a numeric value representing the strength of a causal relation between two nodes, which is estimated using do calculus. So higher the effect weight, higher level of responsibility is assigned to the treatment event for the occurrence of an outcome event. There are three types of treatment effect weights: total causal effect, which is an effect of an outcome when an intervention is done on the treatment. So for the case of this causal relation, C causes B, if the intervention can be done on the node C by removing any of the incoming edges to node C and assigning a particular value that you want to set it. Natural direct effect. This is the effect of an outcome of an intervention on the treatment in the presence of the mediator, where the mediator takes the value of counterfactual equals to 0, so false. So similarly, we can see that we are intervening on C, but the mediator A takes us some different value, let's say C prime. Natural indirect effect is an effect of an outcome of an intervention on the treatment in the presence of a mediator, where the mediator takes the counterfactual value of 1.
A question about
Yes.
this treatment. The I find your definition of mediator to be very broad, you know?
Yes.
So for example, in the network, in the picture, it's unclear to me whether you can call C a mediator. You know, if A is your treatment and, you know, D is your outcome, you can say, okay, B is a mediator, but C it is not really, you know?
Yes.
So would you be able to represent something like that, and how would you do that?
So in the later part of my work, so C is like a confounder for the relation A to B. So these roles are defined within the context. So for A, B, D, I'm just looking at this causal chain of A, B, D, and C is not playing a role there. But I have taken confounders into account in one part of my work, which I've not be talking about it today, but I can get explain it to you.
Yeah, I
after.
know the proposal has something about.
Yes.
Confounding, but it seems to be a little misleading to show that example of causal network, because you don't have a way to represent C in using the three types of nodes you introduced.
So these roles are in particular to the causal relation that I'm considering, not in terms of the entire network. So for a specific relation, what would be these roles assigned by each node?
Thank you.
So representation of causality in knowledge graph. So why we are doing it? Knowledge graph can integrate heterogeneous domain knowledge into a unified representation. It can leverage deep learning methods. It can transform syntactic information into semantic information. So for example, in case of the lung cancer example, lung cancer node is still at the syntactic level. Adding knowledge graph, adding domain knowledge to it makes it more semantically appealing, or give the abstraction of that lung cancer is a type of a pulmonary disease, has the certain medication, can cause dyspnea or short breathing. Knowledge graph also provides a rich context, enhancing the understanding and analysis. So our approach aims to enhance the knowledge graph with these three causal concepts. So it has causal roles, causal relations, and causal effect weights. How do we do that? We define a causal ontology, which is the first to model these three concepts into the ontology or the knowledge graph framework. So this is our first, so we have two different ontologies. This is the RDF-based framework, where we have causal relations are reified as a causes class, and events are linked through this causes relations. And causal relation has this object property of has effect weights. So in this term, it still is a part of a binary relation where a causes can has treatment and event, causes can has out
think this is the last thing that I saw.
Okay.
Yeah.
So maybe start
Okay.
here, Utkarshani.
So I represented causal ontology in two schema, one having just the RDF and another one was RDF star. So this was just the RDF based framework where we represented causal relation as array for class causes, and events are linked through causes using the causal role properties. And causal relation has object properties of has effect weights. We converted this causal ontology, or we expressed this causal ontology as description logic axioms also. On the other hand, we wanted to use hyperrelations, which has the capability of using the RDF star, where we can represent a causal Bayesian network more intuitively in this framework. So in this case, causes relation has hyperrelations of has treatment effect, has outcome, has mediator, and has effect weights. You can see my screen, right? I just want to make sure that this is going on. Okay, great. So for the case of causal hyperrelational ontology, axioms can only be partially formalized in description logic, where the causes hyperrelation would be the domain of the causal event role relation and the causal effect weights relations. Following the ontology framework, we have two different types of causal knowledge graph. So one on the left is a triple based knowledge graph, where the edges representing causal links connects pairs of causal entities. Each causal link is a quad with head, relation, tail, and weights, where HC is the head causal entity, relation is the causal relation, tail is the tail causal entity, and weight and the WC is the causal weight. On the other hand, the hypercausal relation knowledge graph, where the edges represents causal hyperrelation links connecting the pair of causal entities with the qualifier pairs. So hyperrelation links are known as the qualifier pair, where you have the relations as well as the entities associated with it. Yes, Dr. Walter. Yes, please, Dr. Walter. Yes.
I am a little confused by your definition of causal effect weight. In causal stage 11. You seem to be using this in two different ways. Okay. In the slides, you seem to equate this with a causal effect. Say, I used to do calculus. But now you hear, and in other places,
Causal weights.
You associate this with a relation. So it is dangerous, it seems to me, to equate the two things. Because the total causal effect is very much dependent on the whole causal Bayesian network, and is not just the property of a particular relation independently of everything else. Okay? So how do you justify this disconnect, apparent disconnect?
So I've used this relation has effect weight, which is just the name of the relation, which is associated with this effect weight or the causal weight. So causal weight itself, it could be the total causal effect weight, just the number. So each causal relation is associated with this number and using this relation has effect weight.
Yes.
And I've used this synonymously with causal weights and effect weights. So these terms are used synonymously during the presentation, but they do have that's it.
Let me give you a simple example. So suppose you have a treatment T and an outcome O. Okay? The causal effect of T on do
Yes.
or is T of O given do T or something like this. Also depends on other variables in your net. So it is not a property of the two variables T and O alone.
It is the property of the relation. Because in this case, I'm only considering the effect of the treatment on the outcome. But if I want to also include the mediator in account, so where the other effects will come in, the indirect and the direct effect. So those effect weights which are associated with the mediator will also be represented as a hyperrelation along with the mediator relation. So which will become clear using the example. So I have three different representation framework. And I am using effect weights and causal weight synonymously in this presentation. So once defined the causal ontology, now we want to instantiate the ontology to create our causal knowledge graph. So we use the causal benchmark data set called Cleverer Humans, which is a data set of collision videos where there are multiple objects colliding with each other. The objects differ in the shape, size, material, color, and there are 27 different types of collision events which are occurring. So in this video, as we see, there's a brown cube colliding with the purple cylinder rolled to the right. This this video is represented into, is transformed, or the events in this video are transformed as a causal network, where we can see that the event E is causing in event A. So the relations or edges in this network represents causes relation here. And the edges are being annotated by humans, where the edges have a causal weight associated with it. And these weights are ranging from 5 to 1, where 1 says it is some event is extremely responsible for causing the other event, and 1 represents that an event is not responsible for causing the other event. So if we see in this causal network that event E is extremely responsible for causing an event C. So causal networks does not contains information at an instance level. If we talk about in terms of knowledge graph, the network itself does not tell me much about what are the causal roles associated with each nodes, and it does not contain additional context and domain knowledge. So what do I mean by domain knowledge and additional context? So this network is specific to a particular video. So the knowledge about the video, which could be video ID, the knowledge about object in the video. Each object has properties, so shape, color, and material. We also divided or created this event taxonomy, where we divided these 27 different events which are occurring in the data set as a single object or a binary object event. So now transforming this causal network into a knowledge graph. So we do this one-to-one transformation where we added these this is still at the instance level, where we add a causal relations between C to A, B to A to B, and the inverse causal relation from A to C. So C causes A. On the other hand, A is also caused by an event C. We incorporate additional domain knowledge. So what the domain knowledge that we considered was object ID, object property. And we use ontology. So we use the causal ontology that we have defined, scene ontology to represent the videos and the objects included in the videos, the semantic sensor ontology to represent the properties of those objects. So for example, a video ID would include this node C, would also include or event C, event A, and event C and A has participants brown cube, which has their own properties of color, which is brown, and shape, which is cube. So when I say additional knowledge or domain knowledge, this is the knowledge that I am referring to in this particular problem or data set. Now associating causal weights to this representation. So we have two different types of causal knowledge graph, one without the weights and one with the weights. So the weights are represented as hyperrelations. So the one on the bottom represents the weights. So each causal relation has a hyperrelation of weight associated with it. And along with the weights, we also want to represent the mediators. So for example, in this case, for the relation C to B, this should clarify your question, Dr. Viltorta, that for this case, for the relation C to B, this has also been C causes B directly, and also C causes B through this indirect path of A, where we can represent this indirect path as a hyperrelation with the relation that A is a mediator in this case, so has mediator the event A, which is also at the same time abstracting the collision events that are been occurring. So the A is type of a collide node. So along with this mediator, I can also associate, I also associate effect weights. So since this is a mediator, it can also have natural direct effect and natural indirect effect, which I'll show you with an example that I have in the autonomous driving example later on. So yeah, so the causal chain in regular knowledge graph representation, you would just have these relations at A causes B, but using our hyperrelational based representation or our ontological representation also enables us to use this mediator association with it and not just rely on A causes B or B causes C types of causal paths. The context is important, yes. Yes.
So how much information there is to capture information about your event or your situation? All that is not there. If you do not use knowledge graph, you do not connect the concept, instance level information to these knowledge graphs, all that is not there. And the power of all those are necessary to adequately describe the situation on the ground. So you do whatever you may in causal AI, you just can't get there. And as an aside, that semantic sensor network is the word that Corey worked on.
Yes.
So,
Yes,
thank
Dr.
you
Valdarta.
for bringing my attention specifically, but B is a collider, it's shielded because of the link C2A. Why not represent that explicitly as in a relate? B is a collider. Now, what's the advantage of having this kind of representation? At the end, you probably will have to reconstruct that B is a collider to do the computation. Right?
So it depends if what is the causal relational context that I'm considering. So if I just look at this entire Bayesian network entirely and not break it down into this each two individual node basis. If I just look at the entire thing as it is, then yes, there are other properties. As a C could be also known as the confounder. B is a collider in this case. But I want to break it down into 2 to 3 path causal relations, where not just I can predict C to A, but I can also infer that C also causes B. And since we use these causal weights, so I know that C causes B, it's not so responsible than this path from C to A to B. So the causal structure, I'm not sure right now how much collider will help in the problem statement I'm trying to solve. So I want to do causal link prediction. So maybe the collider information, I agree, it can be included in the knowledge graph or those concepts.
Well, colliders are extremely important if you're trying to infer structure from data. And I know you are, that's not your goal, it's stated very clear. Nevertheless, if you ever compare this to baseline, that I don't know, maybe you'll find that in some cases, an explicit representation of collider would have. I don't know. I don't know how far you went with your experiment.
Maybe I can get back to you later. So up until now, we constructed a domain-agnostic causal ontology to express the causal concepts and relations. We established the case for representing causal ontology using RDF star. We constructed 3 causal knowledge graph using this benchmark data set, a simple triple-based, the one with weights, and the one which captures the contextual information using the mediator representations. So we covered the representations. Now we move on to the inference tasks. So can learning from incomplete causal network be mapped to the knowledge graph completion? Can causal weights on the causal relation be used? Can prior knowledge can be used for knowledge graph link prediction? So to do causal knowledge graph completion, we use a knowledge graph link prediction technique, which is the task of predicting new links in a knowledge graph. So a link is in the form of head relation tail, and the link prediction model predicts the missing link of missing elements of these triples. So either we could have a tail missing, relation missing, or a head missing in this triple. So to do so, we train a link prediction model which samples the data gathered from the triples in the knowledge graph. It generates negative samples by corrupting the existing triples. So either it would change the head or the relation or the tail in the triple. Then these knowledge graph triples are divided into training and testing, and a model is trained using the existing knowledge graph embedding algorithm with the link prediction objective in mind. So we used these 4 types of embedding algorithms. So transy, wholly, distant, and complex, which is commonly used in this domain. So our task is to do causal link prediction using the knowledge graph completion. We want to predict or discover causal entity class for the causal relation given. So the existing approach or the existing knowledge graph link predictions techniques, they predict the instance level information or instance level entity. However, we want to predict the instance, the entity class in our case. So to do so, we come up with these we came up with this reified path where we connected in the case of causal prediction, where we want to predict what will be the causes or what will be the effect of a cause entity. In the case of causal explanation, our goal is to predict what caused an effect entity. So to do so, we have a reified path of causes type from the causes event to the effect entity effect event type, and the caused by type from the effect event to the cause type event entity. Adding the reified causal paths to our knowledge graph, both for the simple. Is there a question in the? Okay. So we added.
Question.
Could you please, could you go back one slide, please?
Is this the one, Dr. Hunes?
One. Sorry.
Dr. Hunes, you're breaking up. Your voice is breaking up. I cannot hear you clearly. Are you still there, Dr. Hunes? Is it okay? I can come back to this slide later.
Utkarshani, well,
Yeah.
before he comes back, maybe I have a question. I mean, can you spend a minute explaining why you made that decision? I mean, you
Yeah.
said that you want to predict entity classes rather than, I mean, sorry, yeah, you want to predict entity types rather than instances, but it's not quite clear.
So the reason being causal, the reason being this is basically has to do with the scale. So knowledge graph has multiple instances. So I want to predict not just a particular instance, but the type which has been caused. So what is that a hit event, or was it the move event? I'm not interested so much into the instance, like was it the A ball or blue ball moving the red ball, for example. So it has more to do with the scale, which would give me a couple, multiple instances rather than the class. Does that answer your question?
Right, so you're saying there's far
More
more
instances.
instances?
Yes. So the
types.
farm, yes.
You're not really interested in that level of detail anyway.
No.
Okay.
Yeah.
Utkarshani, wouldn't the relevant causal content be expressed at the class level rather than the instance level? I mean, that seems to me the more efficient way to talk about these things.
So the class level would be more efficient in
Yeah.
this case. So yes, that is true.
And then the instance just inherits.
Information being represented any.
Dr. Hunes, I
But
cannot.
Utkarshani, is there
Yes, Dr.
time information? So when you do causal prediction,
Mm-hmm.
A causes B,
Mm-hmm.
does it make use of the fact that A precedes in time B?
Yes.
Is it possible that you can predict B causes A even though it comes afterwards?
So for that, we are using this caused by relation, which is an inverse relation to do that prediction. Your voice is breaking up, Dr. Hunes.
And I just want to make sure you're not predicting an impossible causality link that goes against time running in a forward direction.
Yeah, I'm making sure I don't do that by using this inverse relation. So causes is always a causes type is always forward. So in that case, A or cause event always appears before the effect event. However, the inverse relation, where I want to say, explain me what led to that effect, is expressed as the inverse relation of the cause, which is caused by. And for the case of type, it's the caused by type.
May I follow up?
Yes,
on
Dr.
question? Yeah, I think Dr. Humes is thinking of what happens in many of these causal discovery algorithms where you do indeed get these impossible errors. I make no sense causally because they go against the error of time. I think some of your references in the proposal, there's at least one reference that addresses this issue, but I wonder whether you actually explicitly represent temporal information somehow as part of your knowledge graph.
So the temporal information is expressed in terms of the causes relation. So causes will always, the causes relation is where the cause event will always precede an effect event.
Yeah.
In case of inverse, it would be a caused by. Okay. And when I'm predicting, I'm making sure I have defined two types of prediction, and causal prediction and causal explanation. For the prediction task, I specify which relation type I want to predict for. So that will always be the causes event, causes type in the temporal order, and the explanation will try to explain the event going in the inverse order or the reverse order. So making sure that that temporal aspect of causality is maintained.
But you don't have an explicit representation of time.
No. But I can. So I can add another ontology, such as time ontology. So this data set does not have the temporal component in it, but those temporal aspects or spatial temporal aspects can definitely be included in the knowledge graph or in this representation.
Thank you.
So we should, so we have two causal knowledge
I,
graphs.
so I have a question, just
Go ahead.
based off of this previous thread. So it seems the representation, the canonical way to represent the relationships between events that may or may not be causal is Bayesian networks. Let's say that for now. And Bayesian network semantics is well defined. And it seems what you're saying is for scale, you want to include information like, let's see if one type causes another, or in some relationship context, some broad class of activity causes another broad class of activity. So my question is, wouldn't it be simpler to just plug in a logical Bayesian network? Those formalisms exist, right? Where you already have Bayesian network semantics. It can prevent things like don't start predicting causes that are backwards in time. That work is already done for you. All you have to now do is include relational information. And
So can I get back to your question towards the end later? I mean, we are
sure.
running
Yeah,
time.
just
Yeah, but we'll get back to you on that.
Yeah.
Yeah, I guess it is 3:11, and we did lose 7-8 minutes because of the network issue. But I think she has a lot more material. We we were able to cut down, but even then, so I think now we'll just request to hold off question until then.
So we have two different types of causal knowledge graph, a simple triple based and the weighted knowledge graph. And now we have added the reified relation here. So if you can see from the top graph, for the relation C causes A, you have this instance level relation of C causes A, but at the same time, you have the abstract or the reified path that A is caused by, in the going inverse order, that the A is caused by move, which is a type of the C. Then A also causes another event, which is B, and the type of the event B, which is the purple cylinder roll to the right, it is of type roll. This is our overall causal link prediction architecture, where we have observational data, domain knowledge, which we learn a causal network using the existing structure learning approaches. So once we have a causal network, we can use causal ontology and concepts from causal ontology to create a causal knowledge graph. And the causal knowledge graph can then be transferred into a latent space of embedding space, which can then be later used into the knowledge link causal link prediction task. So we have two types of embedding, one with weights and one without weights. Our architecture is agnostic of the type of structure learning algorithms that one uses to learn the basic or the first causal network. We evaluate our approach on different types of different graphs with varied domain knowledge, such as type and event. So the first graph on the left only consists of causal relation. The second one in the middle contains the type information associated with the events. And the third graph, along with the type information, also have participating object event information in this knowledge graph. So as per my hypothesis, I showed you the representation of causal ontologies or causal representation in a neurosymbolic AI. We did the inference task that can we learn from incomplete network, that it does, can that be mapped as a knowledge graph completion? For the evaluation, we'll be talking about, can now causal AI tasks be evaluated based on the causal Markov assumption? Does integration of causal weights and causal relation improves the performance? And does integration of prior knowledge improves the performance of causal AI tasks? So what do I mean by causal Markov assumption? This might also answer the question that Dr. Hunes has and Dr. Valtorta has, that am I making sure that the temporal order of these causal events are maintained? So let us say in our case, we want to predict for the causal node G to C, we want to do the prediction, what is the event that G causes. So in the random data set split, typically what you would do is you would divide the data set into 80-20. So training, 80% of the data would go for training and 20% would go for testing, or 80-10-10. However, in the case of this split, which we call as a Markov-based split, it makes sure it considers the Markov assumption, which states that the node is independent of all its non-descendant given the set of its parents. So I'm making sure that any causal relation associated with these nodes C, which is G causes C, C is caused by G is caused by type the event C, and C is caused by type the event G, are set into or are into the testing set and not into the training set. If you put these relations in the training set, it causes the bias because some of these causal relations would already be learned by the model. We evaluated these metrics based on two metrics. So mean reciprocal score rank and the hit, which is a common evaluation metric for the knowledge graph, knowledge embeddings. These are some of our results. So we were able to show that the weighted link prediction outperforms the baseline causal relations by 75% with the Markov-based split. The random split, which is the randomly 80-20 split of the data set, introduces data leakage and model bias with the performance boost of 14%. The additional knowledge, which is the knowledge of event types and participants with weights, improves the performance by 31% in our case. So we showed the representation, we talked about the inference. In our evaluation, we did see that we can evaluate based on the causal Markov assumption. The integration of causal weights improves the performance, and the integration of prior domain knowledge improves the performance of our tasks. So now I showed the performance of this causal neurosymbolic AI representation on a simulated data set. Now I'll be talking about the real world application of it. The application is in two domains, autonomous driving and smart manufacturing. So in autonomous driving, the aim is to improve the driving scene understanding by representing explicit causal relation between entities in the scene. So there are, given this image here, there are two basic causal relations. So a stop line marking causes a vehicle to stop, stop line marking causes a pedestrian to cross. So once we have a causal network which represent these relations in the data set, we can do what counterfactual. So what if there was no stop line marking, the pedestrian was jaywalking, would the vehicle still stop? On the other hand, for smart manufacturing use case, we are interested in doing root cause analysis. So understanding the causal association between objects and events in the assembly pipeline, using causal associations to explain and predict the occurrence of future anomalous events. So for the case of autonomous driving, I use this data set, Panda set, which has autonomous driving scenes annotated with events and objects occurring in this driving scene. So it has the annotations of car, pedestrian, stop line marking, building, barriers, and so on. So taking the same image again, so we can think about this image as a small Bayesian network where the one in the purple is a stop line marking, causes the pedestrian walking here. At the same time, it causes the vehicle to move and vehicle to stop, and the pedestrian is walking is also causing the vehicle to stop. And we transform this this image here as a Bayesian network, and then using the data set, we estimated the causal effect weights. Transforming all that or mapping all that information as a knowledge graph, this is a snapshot of how a hyperrelation-based knowledge graph would look like. So this should answer Dr. Valtorta's question, what if there's a mediator involved? There are other effects associated with that mediator relation. So in this relation on the bottom, we have this relation of causes with mediator, where we have a hyperrelation mediator associated with the pedestrian walking and has these two different types of effect weights, which are only associated with the mediator variable. The causal relation on the top is just the simple causal relation between the treatment and an outcome and has the total causal effect weight associated with it. So using those causal network, I want to answer 3 competency questions. So we take the data set, we created a causal knowledge graph, causal network, we enrich the knowledge graph with the effect weights. Now we want to answer like, how would a stop line marking in the driving scene affects the pedestrian behavior? So now we can query the causal knowledge graph for these questions. So in this case, this question is associated with the total causal effect weights, where we see that the stop line marking has a higher causal effect on the walking pedestrian with object. So Pedestrian with objects seems to be more responsible citizens, following the traffic rules, crossing the street only at the stop line marking, compared to the just pedestrians without any object associated with them, or with them. The second competency question is, what if a pedestrian is jaywalking? How would it affect the vehicle's behavior? So this competency question can be mapped to the natural direct effect, where we see that the jaywalking of an adult pedestrian with object has a positive effect on the stopping of the vehicle. So jaywalking pedestrian with objects has a higher causal effect than jaywalking pedestrians without an object. So the vehicles or drivers tend to be more alert of the walking pedestrian with object. So then object in this case could be a stroller, backpack, or an umbrella. The third competency question is, what if the vehicle fails to identify the stop line marking? How would it affect the vehicle's behavior with respect to the pedestrian? So this is the case where the pedestrian behavior is in accordance with the stop line marking. So there is a stop line marking, but faded, and the vehicle stopped to identify it. So in this case, we see that the effect is higher for moving vehicle than the stopping of the vehicle. So the vehicle will continue to move, failing to identify the stop line marking in the scenes. So we created estimated causal effect weights using the observational data and the causal network. We created a causal knowledge graph from this incomplete stop line marking causal network. We answered these competency questions by querying the knowledge graph. So the next step in this case would be you doing causal link prediction on autonomous driving for the knowledge graph completion. So these are my two future works. As I already explained, for the autonomous driving, in the case of smart manufacturing, the goal is to construct a causal knowledge graph for this rocket assembly data set that we have. This is an in-house data set from the McNair Center, and then using causal link prediction techniques to detect root causes of anomalous event in the smart manufacturing. This is my projected timeline. So this summer, I want to finish the task of causal link prediction in autonomous driving scene. In the fall, I aim to construct the smart knowledge graph from the smart manufacturing data set. For next spring, use the causal link prediction to detect root cause of anomalous events in the smart manufacturing, and hopefully by summer, defend my dissertation. Thank you. Questions?
First, I have a trivial comment about the autonomous driving scenario. The stop line is also